Hi everyone, my name is Syeda Tehreem Haider and I am a final year student of Electronic Engineering from University of Engineering and Technology Rexla, and I am going to present my research article which is titled as Pattern Analysis Framework for Detection of Cardiac Disorders using VCG Signal Analysis, and my co-authors are Engineer Mohammad Umar Khan, Engineer Sumair Aziz, Dr. Mohammad Faraz, Dr. Sayyid Zuhaib Hassan Naqvi, and Gabriel Axel Mortis. This article was presented in 5th International Conference on Advancements in Computational Sciences. So without any further ado, let's move towards the contents. First of all, I will give an overview of our research topic in introduction section, and after that in the motivation section I will highlight the significance of our topic and why is it important to explore it further. In methodology, I will explain the approach we have used in our work, and on the fourth step I will delve into results and discussion, and finally I will conclude my presentation with a summary of main findings. So first of all, introduction section. Well, cardiac disorders exert a profound impact on human health, often resulting in severe and life-threatening situations, including impacts on physiological functions. Well, the onsets of these diseases are attributed to a multitude of factors encompassing infections, diabetes, genetics, addiction, aging, physical inactivity, and others. Symptoms include irregular heartbeat, shortness of breath, angina, pain in various body regions like jaw, neck, back. Well, these disorders not only compromise individuals' quality of life but also pose significant challenges to healthcare systems globally. So, accurate and prompt diagnosis is imperative for effective treatment and reduction of health risks. Next is the motivation section. Well, the staggering stats represent that each 1 out of 4 deaths worldwide are attributed to these cardiac disorders annually. And 4 years back, CVDs were the cause of 19.05 million deaths globally, out of which 9.9% were in USA. Moreover, CVDs have also taken 17.5 million lives in the year 2012. According to World Clinical Trials, we had to face 17.3 million deaths globally in 2015. Moreover, 6 million more deaths will be added to this number till 2030. And according to a survey from 2016, we have seen that almost 31.4% of the global deaths were because of CVDs. We have shortlisted the following classes for our work, including bundle branch block, cardiomyopathy, and dysrhythmia, with one healthy control. And why we have opted for these classes? The reasons are that the diagnosis of these classes is complex and challenging. Moreover, they have overlapping symptoms, and significant clinical expertise is required for their diagnosis. Next is, how can we diagnose? Well, several methods exist for the diagnosis of heart diseases, including echocardiography, stress test, ECG, endomyocardial biopsy, and others. We have selected ECG for our work, and the reasons include that ECG is non-invasive, which means that ECG is safe and comfortable for patients as it does not require any incisions or injections. Moreover, it can easily assess heart rhythm, which means that it can easily locate irregularities in heart's electrical activity. Moreover, it can also find abnormalities in the heart's electrical system. And risk stratification means that ECG waveform analysis helps to assess the risk of harmful cardiac events. Next is Vectorcardiogram or VCG. VCG serves as a comprehensive representation of the heart's electrical activity, having both spatial and temporal aspects information across the three orthogonal planes of the body. And these planes include frontal Vx, sagittal Vy, and transverse Vz, which are also shown in the figures. VCG is actually the vector sum of P, Q, R, S, and T waveforms. And our objective is to make a comparison between VCG and ECG based classification. Next is literature review. We have selected the articles which have utilized the same PTB diagnostics ECG database for the same classes which we have opted. An article from 2016 has used bandpass filtering and machine learning algorithms, SVM having an accuracy of 60% and ANN, which is artificial neural network, with an accuracy of 84% for classifying cardiomyopathy from PTB diagnostics. An article from 2019 has employed continuous wavelet transform and Stockwell transform, achieving classification accuracies of 88.09% and 58.62% respectively for dysrhythmia diagnosis. Another work from 2019 has utilized discrete wavelet transform, MFCC, and k-nearest neighbor algorithm for classification of bundle branch block with an accuracy of 84%. And another article has utilized bandpass and moving average filters alongside SVM, achieving an accuracy of 86.2% for diagnosing dilated cardiomyopathy. And a work from last year has utilized random forest algorithm to classify CVDs within PTB diagnostics with an accuracy of 85.01%. Next is methodology. Well, the following block diagram depicts our proposed method for the detection of bundle branch block, cardiomyopathy, and dysrhythmia, keeping one healthy control. The initial step is to acquire the data from PTB diagnostics. The next step involves the pre-processing of ECG signals. The three sub-steps include VCG extraction, segmentation, and application of empirical mode decomposition, followed by feature extraction and laterally selecting features. And the last step is of classification. So the first step in the methodology is the acquisition of data. We have used PTB diagnostics ECG database and the number of recordings is 549. Subjects are 290, out of which 209 are male and 81 are female. And out of 15 channels of ECG, we'll be focusing on the last 3 channels, which are VCG signals, represented as Vx, Vy, and Vz. VCG having 3 channels. And the sampling rate is of 1000 Hz. The specifications of shortlisted classes: for bundle branch block, we have 17 signals against 15 subjects. For cardiomyopathy, 18 subjects and 20 signals. Dysrhythmia, 14 subjects, 16 signals, and for healthy control, 80 signals against 52 subjects. So the total number of signals under observation is 133. Next step is of signal pre-processing. The sub-step include: step 1 is of extraction of VCG from ECG. We have basically extracted the last 3 channels from 15 channel ECG. Step 2 is of segmentation. Signal length is varying from 30 seconds up to 120 seconds, and we have segmented these signals of variable length in non-overlapping windows, with each window having a size of 10 seconds, and the total number of segmented signals is 1484. These are the segmented VCG signals. Step 3 is of implementation of empirical mode decomposition. Well, EMD is a signal processing method that decomposes a complex signal into a finite set of oscillatory components called intrinsic mode functions, which can easily capture signal's local characteristics in both frequency and its amplitude. Moreover, EMD is adaptive, and it is suitable for analyzing non-stationary and non-linear signals like VCG. And in our thorough pattern analysis of intrinsic mode functions, which are extracted from VCG signals, we have systematically examined each IMF's local characteristics, focusing on the presence of PQRST complex pattern. Our experimental scrutiny has revealed an obvious absence of PQRST complex in IMF 6, 7, and beyond, as well as in the residue, which are also shown in the figures. Moreover, we have analyzed that the higher order IMFs contained comparatively less information content. So we have rejected IMF 6, 7 up to the residue. Moreover, we have selected IMF 2, 3, 4 and 5 as they have featured PQRST complex pattern. Moreover, our experimentation exhibited that IMF 1 contained high frequency noise-like components. So, being informed by these findings, we have reconstructed VCG signal using IMF 2, 3, 4 and 5. Well, next step is of feature extraction. Initially, after observing the pre-processed signals, some features are extracted from the pre-processed signals, and these include time and frequency-based features along with the cepstral domain features. Some notable time features include mean, skewness, kurtosis, RMS value, standard deviation, variance, log energy, and others. And frequency features include spectral flux, spectral decrease, spectral roll-off, spectral flatness, mean and median frequency, and other features as well. Cepstral features include MFCC and GTCC. Next step is of feature selection. Well, we have used several feature selection techniques like MR, relief, F, chi-square, ANOVA, and others. However, the results were not impressive, so we opted for back elimination method. In this approach, stepwise elimination of less significant features is made from the model iteratively until an optimal set of features is achieved. It actually enhances the model's simplicity and model's performance. And the total number of selected features is mentioned, which is 21. The last step is of classification. We have used tenfold cross-validation approach, which is a common practice in machine learning. It actually splits the data set into 10 subjects, using 9 for the sake of training and 1 for testing. This process is repeated 10 times, evaluating models' performance on each subset. Moreover, we have utilized several classifiers, like some classifiers from k-nearest neighbor, KNN, some kernels of support vector machines, ensemble back trees, and wide neural networks. Next is results and discussions. Well, out of all the classifiers which we have implemented so far, Find k-nearest neighbor classifier has achieved the highest classification accuracy of 97.9%, and the TPRs for each class are shown. For bundle branch block, 95%, for cardiomyopathy, 97.5%, for dysrhythmia, 93.9%, for healthy control, 99.1%. Here is a comparison with other classifiers as well. The results of classification based on selected features using fine KNN classifiers are 97.9% accurate, while all other classifiers achieving an accuracy higher than 90% are shown. Well, the reason why fine KNN has outperformed classifiers like SVM and neural network is that KNN focuses on local patterns and non-linearities and can work with a wide range of features. It actually traces the local patterns in the data. However, SVM focuses on global optimization. And for neural networks, they might have faced difficulty in obtaining those localized patterns from PQRST complex, basically, which Find k-nearest neighbor has achieved successfully. Next is comparison with the previous studies. Well, the following table represents a comparison of ECG and VCG based classification methods. Our work is VCG based, and we have made a comparison of our work with the ECG based models. Well, our method has achieved the highest classification accuracy of 97.9%, even with 4 classes under observation. However, ECG based methods, even with 1 class under observation, have achieved less classification accuracy, depicting a victory of VCG based model over ECG based classification method. Next is conclusion. We have successfully applied machine learning approach for diagnosis, which is 97.9% accurate. ECG signals of 4 classes, namely bundle branch, block, cardiomyopathy, dysrhythmia, and healthy control, have been utilized for this work. This study gave a comparison of VCG and ECG based classification. Moreover, our work shows that the 3-channel VCG has done better classification than ECG, having more number of channels, even with 4 classes under observation. Moreover, VCG has offered less computational complexity as compared to ECG, as it has less number of channels. Our future strategy for this work is to expand the number of classes of cardiac disorders along with the balanced datasets. So these are the references, and thank you.